All right, thank you. Thanks for coming, guys. Okay, so what does this talk about? First, I will motivate what is DNS spoofing and why we need a secure name resolution. Then the focus of my talk will be on DNSSEC, because this is what is being deployed right now on a wide range. I will introduce DNSSEC to you, but very briefly, so if you know it, don't sleep away. It will be over in a couple of minutes. Then I will talk about the deployment status. People are using DNSSEC right now, and we'll see how many people are using it. We will talk about the implications. What does it mean when people start using DNSSEC? Then we will talk about the root zone, who controls the root zone, who has the root zone key. And then we will see alternative approaches to secure name resolution. Namely the DNS curve approach by Dan Bernstein, who is also here at the Congress. And you have you might have already heard about DNS curve. He had talks about this, but today you will hear it from a different point of view, which may be also interesting to you. And then we will talk about Namecoin, which is a bit different. And in the end, we will briefly discuss what is Zuko's triangle. Okay, so let's start. I assume all of you have heard of this DNS thing and know what it is, but let's make sure we're on the same page here. So with DNS, your application can ask your operating system, your stub resolver, to resolve a name, and your stub resolver will ask a recursive name server to do the resolution, because the stub resolver really has only a small functionality and can only forward name queries. So the recursive name server does all the work, goes to all name servers, gets all the names, retries if anything fails, and there may be multiple recursive name servers in a chain. So you can have one recursive name server in your local network, or your local friendly admin has one, and your ISP may also have a recursive name server that you're using. And then the authoritative name servers will be asked, the name server that holds the data, and they deliver the DNS zone, the actual data. So DNS spoofing is when an attacker wants to spoof a DNS response to point you to another web page or to another server or whatever. And a remote attacker can try to do remote UDP spoofing by, for example, sending you some kind of HTML link, trigger a DNS resolution on your machine, and then your operating system will query for a specific name, but your operating system or your resolver will put random data into the DNS query. And this is to make the attack less likely to succeed. So the random data will be in the transaction ID and in the source port. So it will be about 31, 32 bit of random data, and the attacker has to guess this data, and if he guesses correctly, the spoofing may succeed. If he doesn't guess it, well, then he has to try again. And this is a very expensive attack, because you need a lot of bandwidth to actually succeed with such an attack. And then there is another type of attack, a local attacker, for example, in a Wi-Fi, unsecured Wi-Fi at a coffee bar. And an attacker is sniffing, and he reads the contents of the DNS message, so we can forge a DNS message or a response to your DNS query, because he reads all the data in it, and he knows the random data in it. And this is a kind of easy attack, and with DNS there is no real mitigation with the legacy DNS, the original DNS, so we need a secure name resolution. Okay, now what is DNSSEC? DNSSEC is a set of security extensions and a couple of RFCs, and it uses cryptographic mechanisms to achieve data integrity and authenticity. But note, not confidentiality, so there is no encryption of the data. And also availability was not a design goal, so it doesn't improve the reliability of the system. And DNSSEC now signs resource records, the data of the DNS, with a private key. And these signatures are then put into the zone. So here you have your name, and then there is a signature. And you, with your resolver, can verify this data by looking up the DNS key, the public key. And how can you securely retrieve the public key? Well, you have to tie the DNS key, your DNS key, with the parent zone, which refers to your name server. And if you tie it all together, you only need the top key, the trust anchor. Okay, here's an example. Oops, sorry. Here's an example of a secure delegation. Here we have a referral from the net top-level domain to some name server. And then we have here a DS record. A DS record indicates that this is a secure delegation. The DS record contains a hash of the public key. So then the resolver can go to the next name server, my IPs are here, and can retrieve the public key and can then hash the public key. It can compare, is this DS record, the hash, the fingerprint of the public key, does it match? And of course, this DS record is also signed, otherwise this would be useless. Okay. Now, DNSSEC signs only resource records, not responses. So negative responses, when you mistype, for example, a query a non-existing name, they have no resource records. There is only an error code and an X domain. So how do you securely can retrieve a negative answer? Well, the solution for this in DNSSEC is this. First, you sort all the names of a zone in a canonical order, and then you sign a proof of non-existence, the NSEC record. And it says there is a name FTP in this zone, and there is a name mail. But in between, there are no names. So you know, okay, when I query for a specific name, whatever is in between, hula boo, and you get an X domain, and you get this result, and you get a signature for it, you can verify, okay, the name hula boo, queried, does not exist. Now there's a problem with this. You disclose all your zone data. Anybody can now retrieve all these NSEC records and get a copy of your zone. And not everybody wants it. Got a small audio. Okay. Okay, everything good? Sorry for the interruption. Okay, now how can we avoid zone disclosure? There is another mechanism, NSEC 3, and this works the following way. You don't disclose the domain names, you disclose hashes of the domain names. So you hash all the domain names in your zone, and then you sort by the hashes, and then you give the following answer. There is a domain name with this hash, and there is a domain name with this hash, but in between there are no domain names. And whoever queries for this name can hash the name that we queried for, hula boo, whatever, will get a hash result and will see, okay, this hash result should be in between these two, but it isn't. Okay, so you know this name that you asked for does not exist. Now there's another problem with NSEC 3. You can retrieve all hash values of a zone, and you can start a dictionary attack, and you can do it offline, so it's way faster than querying online for every existing domain name. So you can still get a copy of the zone, but it's much harder. Okay, now what is this potential secure path of DNSSEC, secured by DNSSEC? Well, we have a DNS zone, which is signed by a private key, and then we could build a stub resolver which does validating and which has a public key, and everything in between is secured. So you have an end-to-end secure path. Now this is not so common. We will look into it in a minute. Usually your recursive name server will do the validation, but we'll get to it. Okay, what is the deployment status of DNSSEC? How many signed zones are there? First of all, the root zone is signed for 2 years. Then we have 100 top-level domains, which are also signed, around 100, out of around 300. And then you see here a selection of top-level domains and the number of signed second-level domains. For example, .nl, the Netherlands top-level domain, has more than 1 million signed second-level domains. It's the largest signed zone. And if you compare this with, for example, the net top-level domain, you will see, okay, there's only 29,000. So it varies. These are probably the best numbers. Okay, now let's take a look at the deployment of validation at stub resolvers. Here you see a list of stub resolvers, and the capability to validate DNSSEC queries or responses. Basically, no operating system, no stub resolver in the operating system can validate DNSSEC queries. However, there is an alternative. You can always run a local name server on your machine. So you can install a bind or an unbound if you don't like bind, or you can even Google for DNSSEC trigger. It's an unbound package with a nice installer. You can install it on Windows or Mac OS X. Yes, Linux too. And it does all the validation. It changes your resolve conf, so you get all in one package. So of course you can install validation on your machine. But the stub resolvers, they are not capable of doing it right now. They are validating resolver libs. You can link your application against it if you want to. And the bind9 package in Debian 7, which is currently in testing, has validation enabled by default. So expect name resolution problems. We will look into it in a minute. Now you may wonder, Windows 7, Windows 8, they read the AD flag. What does it mean? A DNS response, when it is validated by a recursive name server, contains a flag, an AD flag. And this flag says the server authenticated the data successfully. This is like an inverted evil bit. It's totally useless in an unsecure network. So if you're in a local unsecure network, a public Wi-Fi, don't even try to interpret this AD flag. So it has no real use in real life. Okay. What you see here is the statistics of the K-root name server operated by RIPE NCC. And you can see here the number of queries per second. It's around 50,000. And here on the left side, you see the number of queries with the DNSSEC OK flag enabled. And this is around 12,000, so it's about 70%. And this flag, DNSSEC OK, it says, yes, the resolver asking for this name is capable of parsing DNSSEC queries or answers. It does not say that validation is enabled. It only says the software could validate, maybe. So let's take a look at how many clients actually are protected by DNSSEC validation. This is the result of a study of about 80,000, 90,000 clients, which ran over the last 6 months. And you can see the largest validation ratio for clients is in Sweden. It's around 55%, 56%. And you can see here the Czech Republic is number 2. It's more than 30% of validating clients. Probably wondering about Germany, it's around 4%. And the United States is number 3. It has more than 10% validating clients. Okay, so there are not so many clients protected by validation, but it's coming. So this number will probably improve over the next month and years. Okay, now let's take a look at the implications of DNSSEC deployment. DNSSEC does not only add security, it adds also complexity. And it may seem obvious what we have seen here. Some signatures, RSA signatures, some key exchange. How hard should it be? Well, we have here a quote of a Power DNS developer, Bert Hubert, and he thinks DNSSEC is very complicated. And to be fair, there's a response of one of the authors of the DNSSEC RFCs, and well, you see it's a point of view. Okay, now there is another problem, or there is a real reliability problem with DNSSEC, and it is validation failures look like general DNS failures. Let me explain this with an example of a HTTPS error, so a TLS error. We go to a domain, HTTPS, and there is something wrong with the certificate. So we get a security warning. And when we're doing online banking or some security stuff, we know, okay, something is going wrong, let's stop. But if we're just browsing the web for news, to read some fun things or whatever, then we probably don't care, we just click, okay, proceed anyway. With DNSSEC, you can't do this. All your application, your browser gets is a DNS resolution error. It looks similar to this. So you have no way to override it. You have no idea, is my internet connection down? Is the DNS server down? Did the validation not succeed? You simply can't see it. And this is because the interface between the application and the stub resolver, it lacks the DNSSEC information. So there's room for improvement. Now, let's take a look what happens when DNSSEC fails. And this fails too often. 2 days ago, the MIL top-level domain, the military, US military top-level domain, failed because the signatures expired. 2 days ago. Then, APNIC, which is responsible for assigning IP address blocks and also for the reverse lookups, they had a similar problem. So the reverse lookups for several IP blocks were down after a hardware fault, and then some software failure occurred. So in the end, the DNSSEC signatures could not be validated. Only reverse lookup, so probably not that dramatic. Then you can see a list of different other errors. For example, NASA.gov. They made a mistake with the DNSSEC configuration. They had to roll over the keys, but something went wrong, and the whole domain was down. And what happens when validation for NASA.gov fails? Well, there is one large US provider, Comcast, which has validation enabled for all customers, and they have millions of customers. And what happened when validation failed on Comcast resolvers? Well, users said, hey, Comcast is blocking NASA.gov. My friend, he works for another ISP or has another ISP connection. He can access NASA.gov, but I can't. It's Comcast's fault. And actually, it's NASA.gov's fault because they made the error on the DNSSEC zone. So what Comcast is doing now, if they find out, okay, there is some validation error, they try to contact the admin of the DNSSEC zone. And they also use negative trust anchors. So this means they simply don't do validation on this specific zone. They turn it off for one specific zone. So it's not really the best way, but, excuse me? DNS unsec, yeah. But it's like a temporary measure, while not everybody is doing validation, so you don't want to be the ISP which has the DNS failures, while the others don't have it. Okay, and if you want to read more DNSSEC failures, here is also a link, so there's plenty to read. Okay, now let's take a look at system time versus DNSSEC. The keys in DNSSEC, they do not expire. But the signatures, they expire. They have absolute validity periods. This is new. In legacy DNS, there were only those relative TTL values for caching. But in DNSSEC, you need a correct system time, more or less. If it varies by a couple of minutes, maybe a couple of hours shouldn't be too worse. But if you boot your system and your system time is reset to factory defaults, then your DNSSEC validation will fail. And now if you try to sync your system time with SNTP, for example, well, how do you want to resolve pool.ntp.org? So we have a little bootstrapping problem here. And it doesn't help to not sign this domain because the root zone is signed and the top-level domain is signed, so in the end, the DNSSEC validation will fail. So what could you do? Maybe the NTP guys could set up an Anycast cloud, which could be at least used as a fallback. Or maybe DNSSEC validation could be turned off while the system finds out the system time is definitely desync or whatever. So there's, again, room for improvement. Okay, now let's take a look at amplification attacks. You may have heard of it. When you deploy DNSSEC, the CPU load will increase on the resolvers because they do all the validation stuff, but not so much on the servers. Because DNSSEC supports offline signing, so you can do it on another machine. You can then copy the signed zone to the actual authoritative server, and you can also do incremental signing, so you don't need to sign everything every time new whenever you have a dynamic update in your zone, for example. So you can only reassign parts of the zone. However, the network load increases significantly on the servers. This is because all these signatures, RSA signatures, take a lot of space. So now we have a problem. Legacy DNS already had a problem with denial, distributed denial of service attacks. The public DNS infrastructure is abused for amplification attacks. So DDoS attackers use the public DNS infrastructure to amplify their traffic. And this becomes even more effective with DNSSEC because the responses are even larger. And the cause for it is not really DNS, it's IP spoofing, which can be done within botnets. So the solution is also not really DNS, it would be to filter all this spoofed traffic near the source. However, there are currently way too many networks which allow to do IP spoofing, and this won't change in the near future. So you have to do some DNS-specific countermeasure because you can't just do nothing. And there is a countermeasure for this, and this is DNS rate limiting. However, there is a trade-off. When you rate limit, it's a question of effective filtering versus collateral damage by doing too much filtering. So the naive approach would be to just set up an IP tables rule, do some rate limiting, but this is usually bad. This will be either too specific for one specific attack, so then attacker will just change one parameter and your filter will be worthless, or it will be too easy to abuse, for example by locking out your victim, by sending spoofed queries to make the rate limiting, to activate the rate limiting and to filter legitimate traffic from a victim. There is a better approach, it's called DNS response rate limiting. And the assumption of DNS response rate limiting is the resolver has a cache, so the legitimate resolver won't ask 10 times a second the same query, it will cache it. And also, when one packet is dropped, the resolver will retry a couple of times, let's say 3 times, and then it will give up. So what do you do with DNS response rate limiting? First of all, you track the state for identical responses per IP address block. And when you see, okay, there is an identical response and it is now 10 times or a second or so, or 5 times a second, then you turn on filtering. But you slip truncated responses every so and so many packets. The default is every 2 packets slip a truncated packet. Now what does this mean? It means you send a response, but not the full response, not the amplified response, only a truncated one, so there is no amplification. And this truncated response has a chance to receive the legitimate query source. So whenever the filtering is activated, the victim of the rate of the amplification attack still has a chance to send a query and get a truncated response. Not every time, but well, retry, and then it will get after a second or third try a truncated response. And when it gets a truncated response, it will do a TCP retry. And with TCP retry, you have no problems with amplification attacks. So DNS response rate limiting may do some damage, but it's very limited. Okay, and there's one important note. Rate limiting protects the amplification target. It does not protect the amplifier. It does not protect your authoritative name server. So if you have a problem with distributed denial of service attacks, which use up all your bandwidth on your name server, well, use over-provisioning. Use any cast, buy more bandwidth, that's the solution. If you do rate limiting, it won't really help you, it may do more harm. Okay, and also another note, this is not applicable for recursive servers. So if you have a recursive server which is doing recursive name resolution, use IP-based access control. Don't install rate limiting. Okay, now let's take a look at another issue. Let's take a look at ISP wildcard redirects. There are some ISPs which are doing redirects when you query for a non-existing name. So you query for www.example.net, and this name doesn't exist, and you should get an X domain, a name resolution error. Instead, the provider sends you an A record and points you to a web server, and this web server shows advertisements, like here in the top right. So what happens when we deploy DNSSEC? Well, a validating ISP can still add the redirect after validation, but it won't have correct signatures. So when you also validate, you will get a SIR fail. This is a response after validation has failed. So instead of an NX domain, which would be the correct response, you will get a SIR fail. However, this looks identical in web browsers. So you see here a comparison. One is an SIR fail, one is an NX domain, and they look the same in a web browser. So to the user, everything will be fine. And of course, you don't need to use the ISP forwarder. You can just run your own resolver and don't need to rely on your ISP forwarder, which is lying to you. Okay, let's take a look at another redirect. And what happens if this is done by the top-level domain operator? For example, VeriSign was doing this a couple of years ago for the com top-level domain. This would still work. You can still do wildcards in DNSSEC, but it gets very ugly. So if you have a DNSSEC implementation that everything works correctly, try wildcards, you may discover new bugs. And here are 2 examples for it. Okay. Now what happens with another type of redirects with the purpose of censorship? Now when we have a government-mandated ISP redirection, for example, in Germany you have heard the term Zensursula, which was such an attempt to do DNS redirection for censorship or blocking. A validating ISP, again, can still add a redirect after validation. And again, a validating client will get a SIR fail, but now a SIR fail instead of an A record. So the client won't be redirected to a notice where it says you have been redirected, you're doing something illegal, stop doing it. Instead, it will be a general name resolution error, so you won't notice that you have been censored. Okay, and again, if you're affected by this, do not use your ISP forwarders. In general, it is more reliable to not use any forwarders with DNSSEC. There are situations when you rely on a forwarder and this forwarder is not validating, where you keep getting the same response, a bogus response, because the forwarder does not know that it's a bogus response, it's not validating, and you can't really recover from that. So in doubt, don't use any forwarders. Okay, then there is another government censorship method, and it's called DNS injection. And there is a paper in which it is described by an anonymous research group, very interesting, I highly recommend it, it's under number 17. And DNS injection uses deep packet inspection to then spoof DNS responses. However, the current method that is being used, it is being used in mainland China, is very coarse-grained. So for example, when you query for that name, the filter might apply, so you may get a spoof DNS response. And also it doesn't care about source addresses and destination IP addresses. So you query for a blocked domain name, there is some deep packet inspection running on a router, and you get a spoof DNS response. Now you may ask yourself, I don't live in China, why should I care? But this does not only affect Chinese ASs. It also affects networks from other countries. And with any cast which is being used in the root and in top-level domains, your packets may take strange routes. So you actually you might be routed through a Chinese AS. It's not very likely, but it can happen. And this study in this paper suggests that open resolvers from over 100 countries have been affected by this DNS injection, which only takes place in China, but affects through Anycast and through routing issues also other countries. The original packets do not seem to be suppressed. So you get a spoof response and you get the actual response currently. So DNSSEC validation would protect you from this type of attack. You would get the spoof response, doesn't validate, okay, throw it away. Get the next response, okay, this one validates, correct. However, when they decide to turn on suppression, so when they decide, okay, send only the spoofed response and filter the correct response, it will depend whether DNSSEC will really help. If you are within an AS which uses this censorship method, then, well, you have no other routes, no transit paths which aren't censored, so we have lost. But if you're around China, in one of these countries that may route through China, you will have a chance to throw away the spoof response and to ask another name server from the set of name servers. Because there's a redundant set of name servers for the root zone, redundant set of name servers for the top-level domains. So when you get a censored response, you can try another one and maybe you're lucky. So DNSSEC may reduce the harm that is done by this censorship method. Okay, let's compare X509, the TLS SSL certificate structure, with DNSSEC. With X509, there are more than 600 organizations that are allowed to create certificates that are trusted by your web browsers. And more than 1,500 root CA certificates are actually trusted by your web browsers. And the problem with X509 is you can't really delegate only a part of a trust. So you can't say, okay, let's say this CA is only allowed to issue certificates for this and this domain. This is not possible. If you have a CA, it can issue certificates for every domain. Now, what could change with DNSSEC? With DNSSEC, there is an RFC. It's called DANE TLSA, and you can put TLS certificates into the DNS. With DNSSEC, trust is limited to one domain, so the COM top-level domain can't mess up with the org top-level domain. However, the DNS root can mess with anyone. So the pro is the trust in root is now limited to one organization instead of 600 CA organizations with X509. The con is this organization gets very powerful, and it's the ICANN. So I don't know whether this is a good idea. At least it's an alternative to X509. Okay, let's take a look at the trust anchor. It's a public root key that you're installing. And let's take a look at who can actually forge answers which should come from your second-level domain. The root zone operator can forge answers because the root zone is asked with the full name. So for example, www.example.net, this query goes to the root zone, and the root zone operator could mess with it, could spoof a response. The registries or the top-level domain operators then can do the same, and your registrar where you registered your second-level domain could also mess with this, because you need to submit your DS record, the hash of your public key, to the registrar, and the registrar could simply change it. Now you can change the trust anchor configuration in your resolvers. You can put specific domains in the configuration, and you can also put keys for alternative DNS routes. So alternative DNS routes are still possible with DNSSEC. Of course, you have to configure the trust anchor manually. Okay, trust anchors can be changed automatically if they are updated. However, you need to install the initial trust anchor by hand. So the initial key must be installed by hand, and then you can do automatic rollovers. Okay, now who controls the root zone and who has the key? The top-level domain operators, when they have a change which needs to be submitted to the root zone, for example, name server address has changed or contact has changed, they submit it to the ICANN. The ICANN is performing the IANA function, and the ICANN sends it to the NTIA, which is a department of the US government. And the US government must approve every change to the root zone. And if the US government approves this change, it sends it to VeriSign, which is the operator of the A root server, and VeriSign creates the actual root zone, the actual assigned data. Now ICANN is in possession of the root key signing key. This is the top-level key. This is the most important key. And it has created this key, and it uses this key to sign the zone signing key. This is a level right under the KSK, under the key signing key. So VeriSign uses a zone signing key, the ZSK, to sign the actual root zone data. And the reason for this, for having two keys, and this is common in DNS, like you have this also with your second level domain. You have a KSK which is changed, which is changed rarely, and you have a ZSK which you can change often to improve security. Okay, so we have the ICANN with the KSK, and we have the VeriSign with the ZSK. Okay, now where has the KSK been created and where is it stored? There are two ICANN facilities in commercial data centers. These are not actually ICANN facilities, these are data centers, but ICANN has rented some room in it. There is one facility in US West and one in US East, both US. And ICANN creates the KSK, ICANN signs the ZSK, which is brought by VeriSign, and also trusted community representatives are involved in this process. Trusted community representatives chosen by the ICANN, which are there to oversee the process, to make sure everything is working correctly, and to say, yes, I've seen this, and they created the key in the right way. And here are some pictures of the KSK key ceremony. There are also videos online, so you can check these references here and watch the videos. You see there is a room with people, with trusted community representatives. There are armed guards, so don't try to get into the data center, you will probably get shot. And they are using hardware security modules to create the key and to do the signing operation. Hardware security modules store the key inside, and they are thought to be more secure than an actual machine. So if you try to tamper with this device, it will delete the key. That's what the manufacturer says. Okay. There was a comment that deletes sometimes the key even when there is no tampering. Yes, when you have some voltage issues, you can also trigger this deletion process. Okay, so where are the keys then stored? The HSMs are inside these safes. And well, the trusted community representatives have also access to these safes when there is a key ceremony. We will discuss this now. Okay, so we have 4 HSMs with 4 copies of the private root KSK key. Okay, how to access or to activate the private key inside the HSM? You need smart cards. There is a set of 7 smart cards west and a set of 7 smart cards east, and you need 3 out of 7 smart cards to activate the HSM and to do some signing. Okay, where are these smart cards? The smart cards are in a safe and in boxes for which you need a physical key. So there are 7 physical keys for West, 7 physical keys for East. And these physical keys are distributed to the trusted community representatives. So there are also backup keys. They are stored on smart cards. So when the HSMs have hardware faults and you can't use the HSMs anymore, there are also 4 smart cards, 2 East, 2 West, which have the private key stored in an encrypted form. And to decrypt the private key, you need also another set of smart cards. This is shown here. 7 smart cards, and you need 5 out of 7. And these smart cards are distributed to community representatives. So the trusted community representatives don't have direct access to the key. They have only access to the key when they are invited by ICANN. And what you can see here is, in the gray area, what is stored in the ICANN safes in the data centers. The HSMs are there, the backup cards are there, the smart cards are there. What is distributed to the trusted community representatives are the physical keys and the smart card to decrypt the backup smart cards. Okay, so here are some details for you to read later on. With respect to time, we will skip this and go to the next topic, and this is DNS curve. DNS curve is an alternative concept to secure DNS. It uses, the most obvious change is it uses elliptic curves instead of RSA, and it is far less complex. It does not introduce any new DNS resource records. There are no DS records, no DNS key records, no signature records. And the keys are also associated to name servers, not to the zones. This is the difference. And DNS curve secures the link between one authoritative server and one resolver, a direct link. And unlike DNSSEC, there is no end-to-end security. So you have to make a connection from your secure resolver to the authoritative name server. You can't use multi-hop forwarding. And DNS curve also uses online cryptography instead of pre-generated signatures. Okay, this is the secure path of DNS curve. Again, link between one recursive name server and the authoritative name server. There are no ISP forwarders in between. You can't use them for forwarding. And also the keys, the private keys, are on the name servers. And each name server can have a different key. But you can also use the same key on all of them. Okay. DNS curve messages use also UDP port 53, but a new custom message format, which is not compatible with legacy DNS. It supports also TXT tunneling. It tunnels all data in TXT resource records. This is to go through strict firewalls, which are looking into DNS packets and verify whether this is really a DNS packet. And DNS curve works the following way. It puts the legacy DNS message, the unchanged DNS message, into a crypto box. And this crypto box is encrypted, it is signed, and this crypto box is now part of a packet, and this packet contains a nonce, a random number used once, and this packet is unique. So what does this mean? This packet is unique, so you have no validity periods. It is read once, and then it is forgotten. Replay attacks are not possible this way, when the nonce is really unique. There is no expiration of signatures, and the system time doesn't need to be correct. So when NTP has some issues, or you have some issues with NTP, whatever, DNS curve will still work and verify everything correctly. And also, NX domains is secure without NSEC or other data, because you encrypt or you sign the whole packet, so NX domains doesn't need any additional data for extra signatures. So a bonus of DNS curve is that the crypto boxes are encrypted, so you can't read them by eavesdropping. However, this is only a small privacy gain, because you can still see the IP addresses of the name servers that you're talking to. You can still see the server name in a TLS handshake, so it's nice, but it's not really that huge improvement. Okay. What kind of cryptography is used by DNS curve? It uses a networking and cryptography lib, pronounced SALT, and it uses elliptic curves for the Diffie-Hellman key exchange, 255-bit public keys. The security level can be compared with RSA 3000-bit, and in general it should be faster than RSA. There are some disputes about performance, but in general ECC is faster because it uses shorter signatures. Then it uses also a shared key. It uses this elliptic curve key exchange to generate a shared key between resolver and name server, and this shared key is then used to do the actual signing and encryption operations, and it can be also cached and reused later. So if one resolver is communicating with the same server, it can reuse one shared key. Okay, how do you get the keys? The client transmits its public key in the query, so the server gets it, and the server encodes the public key as server name in the parent zone. This is shown here. You have here a delegation for example.net and delegates to some server, and here in the server name we have the public key of the DNS curve capable server. And this is put in the parent zone, in the top level domain, for example. So you don't need extra resource records for the key, and it will be secure if the parent also uses DNS curve. So you need only, again, for the root zone, like a trust anchor. Okay, now let's take a look. Could we deploy DNS curve in the root zone? This is a map of root name servers, all Anycast instances in the world, more than 300. Do we really want to put the private key on all these servers? Well, think of the DNS injection attacks. You certainly don't want to put the private key in every country. And this is the reason why DNS curve cannot be deployed on the root zone. ICANN does not want to distribute the key everywhere. The US government also doesn't want this. So DNS curve will never be used in the ICANN root zone. Okay, the private key must be online on the name server. It's not feasible for root, also not feasible for major top-level domains, which are also using Anycast, which are also distributing the name servers in many countries. And what does it mean when online cryptography is being used, online signing? Well, you could try to do a CPU exhaustion attack on the authoritative name server. The question is, does this really have an impact, or is ECC this fast that it doesn't really matter? Well, it's unsure. I can't answer this. Maybe Dan has some data on this. The response sizes of the name servers increase slightly. You need to send the crypto boxes, but it's only a minor amplification factor, so it's comparable to legacy DNS. So it doesn't make amplification attacks worse, like DNSSEC does, but it also doesn't solve them. So amplification attacks are still possible, but not with such a huge amplification factor. Okay, we have no multi-hop caching. So what will this mean for the load on the top-level domain name servers when we have less caching? Unknown, I have no data found on this. And what's interesting, DNS curve happily carries also DNSSEC signed data, so you can use both. Transport DNSSEC signatures within DNS curve. But unfortunately, you can't use DNSSEC in the root zone and in the top-level domain zone to securely retrieve the public key of DNS curve. And this is because DNSSEC does not sign everything in a delegation. The server name is not signed, only the DS record, only the fingerprint. So it's a bummer, but no. You have to implement a server which uses both DNSSEC and DNS curve, and which then changes from DNSSEC to DNS curve or whatever. It's not really useful. So an open issue is how to securely retrieve the DNS curve public key. This is not solved yet. Okay, we are short on time, so let's move on to Namecoin. A Namecoin is a peer-to-peer based naming system, and it's very different than what we have seen with DNSSEC and DNS curve. Namecoin is based on Bitcoin. It's actually a fork. And it uses a namespace which is controlled by a peer-to-peer majority and not a centralized instance, like, for example, the root zone. Okay, so we have miners who generate namecoins, like in Bitcoin. Users can send namecoins to each other, like in Bitcoin. And all transactions are publicly shared by all users. And now Namecoin introduces new transactions to store and update name data. So you can store arbitrary name value data, 255 bytes for the name plus 1023 bytes for the value. And the primary use case is to put into these fields DNS-like data. So you could put also your GPG signature in there. It's also possible. And each of these transactions costs a small fee, like in Bitcoin. You need to refresh the names. They expire if you don't refresh it, and this will also cost again a fee. Okay, how can you resolve Namecoin names? All domain names are organized under a virtual .bit top-level domain. This top-level domain doesn't exist. It's not in the ICANN root. And it's also not applied for in the new GTLD problem, so it won't be in the ICANN root for the next couple of years. Now, all users in the Namecoin peer-to-peer network share a copy of all names of the whole Namecoin database. And Namecoin, like Bitcoin does, ensures the integrity of this. So you can do, when you participate in the Namecoin peer-to-peer systems, local secure name lookups. Now the question is, how can outsiders resolve .bit names? For example, your mobile device. You can't really go with your mobile device in a peer-to-peer network and stay online all the time. So there are approaches for this, DNS gateways to the Namecoin namespace. And there are two methods to do this, and one is bad and the other is worse. The first method is you configure a domain search suffix in your operating system to point to a Namecoin DNS gateway. And whenever you type in a .bit name, your resolver will first go to DNS. It will find out, okay, .bit doesn't exist. You get an NX domain, and then your operating system will append this suffix, and this suffix will point to a Namecoin DNS server, and the resolver will now retry to resolve this name. And this is bad because some guy on the internet running this Namecoin DNS gateway will get all your NX domain queries. And the other method is to use directly a Namecoin DNS gateway as a resolver. And this is bad because this guy on the internet will get all your DNS queries. Don't do this. There is also no secure way for outsiders to resolve .bit names. So there is no way to get DNSSEC signed data or another kind of signature. So this outsider resolution is not secure. It's only secure if you participate in the Namecoin P2P system. And it's also incompatible with DNSSEC because the root says there is no .bit, and the root says it's securely. Okay. Last slide. Let's take a look at Zuko's triangle. What is Zuko's triangle? Think of what are desirable properties of a naming system. You want a naming system to be secure. You want a naming system to be decentralized. You want a naming system to use new and meaningful names. So not random names generated by some secure random number generator. And now the claim of Zuko's triangle, of Zuko, it's a peer-to-peer hacker, the claim is any naming system can fulfill at most 2 of them, of these properties. And an example for this is DNSSEC. With DNSSEC, you get a secure naming system with human meaningful names. You can choose your name, whatever you want. Yes, if a name is taken, then you can't choose it, but well, choose another one. But it's not decentralized because it's hierarchical. And the root is very powerful, so the root can mess with anyone. So it's not decentralized in the way that Zuko meant it. Now let's take a look at Namecoin. Namecoin is a decentralized network. It doesn't use a hierarchical structure. It uses human meaningful names, if the namespace is not spammed. And it's also secure if you participate in the peer-to-peer system. So it actually achieves all the 3 properties. However, think of what about scalability and what about efficiency. You need to participate in the peer-to-peer system, and you need to copy the whole data of the namespace of Namecoin. And this namespace might get large. So there are some scalability and efficiency issues, and that it solves all 3 properties doesn't mean that it's really better than DNSSEC or DNS curve. Okay, so let's conclude this talk. We have seen a lot about DNSSEC. We have seen alternative name resolution approaches, and decide for yourself what is the status of secure name resolution. Is it this one or is it this one? Thanks for listening.
Thanks, Matthias. It's an excellent presentation. So I'm sure we have a lot of questions. I know we have a few from the internet already. So if you have a question, please go over to the microphone over here or the microphone over here. And while we're waiting, let's get a question from the internet.
Thank you very much. A user on the internet commented and asked for your feedback on the thing that since about 3 to 4 months ago, .com, .net, and .org have broken proofs of non-existence through NSEC and NSEC-free records, even though they are present in the answer. Can you care to comment on that matter?
I don't really know about this. Well, DNSSEC failures occur. Administrators make errors, and DNSSEC has a lot of opportunities to make an error. So what we need to do is the DNSSEC tools, the administration tools, need to mature, and the admins need to get better. Unfortunately, DNSSEC does not improve the reliability. It's getting worse.
Thank you. Question from the room?
Okay. One question, you said that it is not possible to connect the bit namespace with other namespaces in a secure way. Am I right about this?
No, I didn't mean this. Right now, the way it is currently implemented, it is not securely implemented. You could design a secure way, and I'm sure people are working on this. Do you mean this?
Yeah, because I think the secure way is to use your own local DNS server and to use a specific forwarder to the bit namespace and at that point to the bit name server, and that would be secure or not?
Yes, you can implement it in a secure way. However, it has to be done.
Yeah, okay. So that's the configuration issue then, more or less.
Well, how much effort do we want to put it in it? It's a question of somebody has to write it first. No?
I don't think there's any code needed because you can do that with a standard DNS server.
Yes, if you run a Namecoin node yourself.
No, if you run something like Unbound or Bind and define a forward stub zone that points to a Namecoin-enabled name server.
Yes, but the Namecoin resolution is not secure then.
Okay.
Okay, so still some room for improvement there, but right, it can be done, yes.
Yeah. Okay, thanks.
Thanks for your question. Another question from the internet?
For clarification command, in X5.09 you can do domain name constraint. So the Mozilla root is actually has now just one for a reason we added Greek domain, but we hope to see that being used more often in the future.
Okay, there was a comment, X509 has an extension to constrain the namespace that is delegated to a specific CA. Yes, I've heard about this. However, it is not widely implemented to my knowledge.
Yeah, the NSS library used in NSS, in Mozilla.
Well, thank you. The NSS crypto library used by Firefox and other Mozilla software does use it.
Oh, okay, so, and it's deployed in the real world?
Yes.
Okay, great.
So Mozilla already has a Greek domain, the Mozilla root CA list has one recently added Greek CA, which is only, I believe, constrained to the .gr domain. It might also be okay for .org, but I forgot that detail.
Okay, that's good. Let's hope other browser vendors will also jump on the train. Thanks.
We have another question in the room? No.
Hi. Thank you for the good overview of the name server solution systems out there. I've been working with NSEC for about 10 years now, and I have a few comments about NSEC and NSEC 3 and other stuff. Using NSEC is okay, because if you believe that you can put secret data in your DNS infrastructure, you're doing it wrong.
I agree.
So the main feature of NSEC 3 is the opt-out function, where you can actually, if you have a huge domain, such as for a TLD, you can sign not all your data, but just some of it that is considered secure.
Okay. Yes, it's a performance optimization. Thanks for this.
But performance optimization is good on that scale, but it can use a lot more CPU on the authoritative name service, because the authoritative name service has to do a lot of work to produce NX domain answers.
Yes.
For the next 2 years, we will also have 1,400 new GTLDs added to the root zone.
Yes, we will.
All of those will use the NSEC.
Is this enforced by policy?
Yes.
Okay, so we will have a lot of DNSSEC failures in the next 2 years.
Yes. But using the NSEC is still a good thing, but we need better tools for that.
Yes,
of course,
that's true.
and better monitoring on that TLD level, at least. I had another comment, but
maybe we can do it offline.
We can talk afterwards.
Can you say a name?
Patrick Hallström.
Okay.
I work with the Open DNSSEC project.
Oh, cool.
So we have time for one more quick question. Is there any question from the internet? No questions from the internet. Questions in the room? All right. Thank you very much, Matthews.
Thank you.